Thank you all for being here. I'm Caroline Gooden. This is Isha Lee. We're going to talk with you about measurement and variance today. What we'd like to do is run through the conceptual portion of measurement and variance, and we'll pause for questions, and then we'll talk with you about an applied example from one of our data sets. So this afternoon, we're going to look at measurement and variance, as Dr. Tolan said. First, we're going to define what is measurement and variance, especially in relation to today, we're talking about measurement and variance with categorical items. We're also going to look at why is testing for measurement and variance important. What are the levels of measurement and variance? There are 5 that we'll talk about today. How is it tested? We'll talk about how we model for measurement and variance. And lastly, we'll talk through an applied example. So first of all, what is measurement and variance? This is a diagram that we'll refer to frequently through the day, and I want to just walk you through a general overview of what measurement and variance is. Basically, it's a technique, a modeling technique that we use that helps determine if the same unobserved or latent variable is being measured the same across groups within a confirmatory factor analysis framework. Again, we're focusing today on measurement and variance with categorical indicators. We can also do measurement and variance across time. We'll talk about that another time. So looking at our diagram, just to give you a rough idea of how we work through the procedures of doing measurement and variance, we start with a latent variable. So the latent variable Sisha is pointing out to you is the item in a circle, in an oval. So for our particular example, we're going to talk through an example of a language scale that we use for young children. And so we're focusing on the latent construct of language today. That language construct had 4 items in our scale. So there'll be 4 items that we're talking about. Those 4 items were categorically scored on a 4-point scale. So we'll be talking about item thresholds between 4 thresholds for each item. We also have item intercepts on our diagram here. That's basically the item mean. And at the bottom, we have the item error, or the variance term. So these are the terms that we'll talk about as we talk about how to set up procedures for measurement and variance. Again, the latent construct, the items, the means, and the error terms. And we'll refer to this as we talk about each step of the way. So why is it important to test for measurement and variance? When we have evidence for measurement and variance, and it happens along a degree, a continuum, which we'll talk about, if we have evidence of measurement and variance, we know that we can make meaningful comparisons between groups, such as between girls and boys. We also know that we're measuring the same trait across groups. So in our language scale, we know that boys and girls are measuring the same language latent trait with our group. We also know that group differences reflect true group differences and not an artifact of test invariance. What if there is no evidence for measurement variance? And it's possible that we run through the procedures, we do the procedures for measurement variance, and it's possible that we don't get evidence for measurement variance. What do we do then? What does it tell us? And this does happen, for sure. First of all, we know that scores from multiple groups don't represent the children's latent ability really well. So if I don't have evidence of measurement variance, I can't say that boys' language skill scores are equivalent to the girls' language skill scores. Also, if we don't have evidence for measurement variance, we know that observed group differences cannot be assumed to be accurate. So if I see a difference in boys' scores from girls' scores, I can't assume that it's due to a difference in their language ability. It's some other artifact of my scale. And lastly, if there's no evidence for measurement and variance, my findings may be unsubstantiated or even invalid. So again, it's important that this be a preliminary step that we do before we conduct our major analyses. Why don't some studies test for measurement and variance? And you'll read studies where they haven't done any measurement and variance testing. Sometimes it's a result of a small sample size. You need an adequate sample size to do measurement and variance testing to be sure that you have trustworthy results. And sometimes it's a lack of knowledge about how to test for measurement and variance. So if a researcher doesn't know how to do these procedures, they may skip this step. But we're going to propose to you that it's a really important step that we all learn and practice in all our research. So some examples where measurement and variance is used. We can compare different groups across the same instrument. So again, with our instrument that looks at child language, we can compare several different groups on their scores on language. We can look at them by gender, we can look at them by race and ethnicity, or by age, by treatment condition, These are examples of the things that we may look at with measurement invariance. And there can be any other variables of interest that you have in your data set. So let's look at, again, the 5 measures, the 5 levels of measurement invariance. These are the levels as labeled by Grimm et al., and they talk about the procedures and the strategies that are used for measurement variance. We're using their terminology today. You'll read slightly different words for these levels. We're using their language today. So the very first level of measurement invariance is dimensional invariance, and we're going to talk about what each one of these levels is in just a minute. Dimensional is the very basic level. The next level is configural invariance. The next is weak factorial invariance, and then strong invariance, and then lastly, strict factorial invariance. And we'll talk in detail about what each one of these levels are. Note that it's a hierarchical procedural analysis. If I don't find evidence for dimensional invariance, that's when my testing stops. If I find dimensional and configural, then I'm going to go on and test for weak factorial. So it's definitely a hierarchy, and at any point, if we don't have good model fit, that's when our analyses, these procedures stop. So to look at the 5 levels, spend a little bit of time on each one. The first, dimensional invariance, a lot of times researchers will actually skip this step. And what it looks at is usually done with exploratory factor analysis. We're looking at, do we have the same factors across groups? So does my one group have language factor as well as does my second group have items with a language factor? It's basically what factors are present. What's the factor structure for my scale? So typically, again, as I said, this is done with exploratory factor analysis. We look at how many factors are in our scale. For the example that we're talking about today, we simply have 1 factor, language, and 4 items. You're going to see these bulleted items for each one of our 5 levels, and I'm going to talk about each one as we go. So again, we're on the first type of invariance, which is dimensional, and so we're looking at the latent factors, the number of latent factors in our scale. This is a conceptual representation of dimensional invariance. Teacher's going to show you, again, point out to you, when we're looking at is the latent factor structure the same, we know with our scale, with our example scale, we have 1 latent factor for both groups.
Okay. So just to repeat what Caroline already showed. So this eta 1 and eta 2 are the language factor for both groups, for boys and girls, if you consider boys and gender as a grouping variable. And the lambda 1, and lambda 1, represent the item factor loading for both groups. And the U12 and U11 represent the item unique variance or item residual or measurement error for first item. And this triangle is the intercept, or it is when we consider this as a dichotomous or binary variable, 0, 1 variable, this represents the threshold, the only one threshold for each item. And this phi 1 and phi 2 represent the factor mean for each group. So basically, we want to make sure all those lines and the parameters are equivalent and comparable for both groups, so that we know that anything we compare at this place is meaningful.
So now we're going to talk about levels 2 through 5. These are the levels that you'll typically see done in measurement analysis procedures. These are done within the CFA framework, as opposed to the first level, which is typically EFA framework. So these are all done within CFA. We did our analyses in Mplus. And the first one that we're going to look at is what is configural invariance and how is it set up. This is a summary of these 2 through 5 levels that we're going to talk about one at a time. And what you can see here, this is actually how we set up our modeling. So for each level, you'll see each level of invariance on the left, and then you'll see which of the items we either let vary or that we constrain as we move in complexity amongst our levels. And we're basically looking at whether we constrain the factor loadings, the item thresholds, since we have categorical data, we're talking about the item thresholds, and the item residuals or the error terms. So with our first level, configural invariance, and this will begin to make sense as you hear all 5 levels, I promise. With the configural invariance level, we let all of those, the item factor loadings, the item thresholds, and the item residuals, they're all allowed to vary. Leave them freely estimating. When we look at the weak factorial invariance level, we then constrain our item factor loadings. And you'll begin to see a pattern here. We leave the thresholds and the residuals free to vary. When we look at strong invariance, now we constrain both the item factor loadings and the thresholds. And lastly, when we have strict factorial invariance, we hold equal the loadings, the thresholds, and the residuals. Then when we get that level of invariance testing, we know that we have a measure that has strong invariance, strict invariance. So this is, again, an overview of where we're going, how we're modeling. So talking more about configural invariance, this is the second level that we talked about. When we're looking at configural invariance, we know that we have the same latent factor across groups. I have one language factor in group 1 and one language factor in group 2. Now I'm looking at, do I have the same item factor structure? Do I have the same 4 items with this factor that I have the same 4 items with this factor in my 2 groups? And it looks like this. Sisha, do you want to explain this one as well?
Sure. Basically, we want to set up the lines to be the same. So the same set of items are loaded on the same factor. This looks comparable or equivalent to the previous step for a unidimensional model, since we only have one factor here. But in case you have 2 factors, what we set up here is we want to make sure the same group of items are loaded on the same factor for both groups. This step would be more unique for when you have multiple factors than the previous step.
So our next level of measured invariance to look at, if we get evidence of configural invariance, we're going to move up and test at the next level, which is called weak factorial invariance. At this level, we look at holding the factor loadings equal across groups, and we look and see if we continue to have a good model fit, and if we do, we know we have evidence of this level, and we'll show you what this looks like. So as you can see, go ahead, teacher.
Yes, basically we set up the lambda 1, 1 here equal to lambda 1, 2. Lambda 2, 1 equal to lambda 2, 2. The second number represents the group number. The first number here represents the item number.
So when we have evidence for measurement invariance at this level, we know now that we have the same factor structure, the same items with that factor, and we know that the factor loadings are also equal. So at our next level, which is called strong invariance, at this level we now hold the item thresholds equal across groups. And I'll show you what that looks like in our diagram.
Okay, so basically we look at the threshold. When we have a binary variable and one threshold, we want to make sure the tau 1, 2 equal to tau 1, 1. It's the same for the rest of the items.
So as you see the progression, now we have the same factor structure, the same items with the factors. We know that the factor loadings are equal, and then we also know that our thresholds are equal. So we're getting more and more evidence that this construct is being measured the same across our groups. So lastly, we have strict factorial invariance. This is the highest level of measurement invariance that we can achieve. At this level, we look to see if our item residuals, if we hold them equal, do we still have good model fit across groups? So we're looking at the error for the items. And it looks like this.
So basically we're looking at the very bottom circles here. Make sure they are the same for the both groups.
So we now have the same factor structure, the same items with the factor. We have the same factor loadings, thresholds, and our error variance are also equal. So the implications of achieving factorial invariance, to whatever degree we're able to show it with our scale, are listed here. We'll talk about these briefly, and then we'll talk about our example with you. So if we have evidence for configural invariance, we know basically that we have the same items loading on the same factor. If that's the level of invariance, if we only reach that minimal level of variance, we have to conduct separate group analyses. I can't say that my girls' scores are equivalent to my boys' scores, so I report them separately if this is as far as my variance measurement goes. We cannot make group comparisons or full group analyses for either the observed or latent level if this is as much evidence as I'm able to achieve. If I get evidence for weak factorial invariance, we now know that we can compare the variance and the covariance for my groups at the latent level. using structural equation modeling. If we get evidence for strong invariance, the implications are that we can compare the mean, the variance, and the covariances for the latent structure, latent factor, again with SEM. And lastly, if we get strict factorial invariance, we know at this level that the group differences that we see in scores actually reflect our latent variable. We can compare means observed and variances, covariances, and means for our two groups. Questions on the conceptual portion before we walk through an example?
We have about 2 minutes of questions, so we can move on.
Yes?
I have two questions. The first is, do you report them all? Like, let's say you got all the way to strong. Would you report each
Yes.
level or only strong?
Yes, report each one as you go.
Each report. Each one
Mhm.
is good. Okay. And then somebody else has a question. But this is the worst.
Sure.
Do you have to do them all?
Well, what I would like to get to, the goal is to get evidence of strict factorial. So I want to do them all.
Will some people choose to stop at a certain level and not even continue testing?
Well, what we said originally is that a lot of times what has been happening what has happened previously in research is that a lot of folks only did a dimensional invariance. That was typically what was done. There's more and more emphasis now on walking through the next 4 steps to look for evidence of configural, refactorial, and so forth. So to give evidence of measurement of variance with my scale, with my data set, I want to get as high evidence as I can so that my results are valid.
If you don't have enough evidence at the lower step, you probably won't be able to proceed to the next level. That's why people stop at a certain point.
So in the most recent slide, having the implications, the difference for what kind of tests you can do between the 4th and 5th level is this saying that you can only do like compare means of in like a classical test theory sense only if you have the strict factorial invariance, but you can kind of do some of that stuff in SEM if you're at the strong invariance level? Is that what those last 2 levels mean?
Yes, with strong invariance, the best thing you could do is through analyze your data through SEM and make group comparisons based on the latent factors, but you can compare means, variance, and covariance. But if you have strict factorial invariance, that's where you could actually compare your raw score or total score or mean score. Then you don't have to go through the SEM, and you can make any comparisons confidently, because the only source of the difference is the true difference.
Okay, we're going to walk you through an example now.
Okay, here is the example we have. We choose gender as a grouping variable and make group comparisons on gender. And this is a child assessment from, we focus on the language domain of this child assessment. And there are 4 items we included, and each item has 4 developmental categories. So for an item has 4 categories, it means it has you will have 3 thresholds. In order to make model comparisons, we look at this set of criteria. So first, for categorical data, there are not so many analyses, simulation analysis on what is the best criteria. But based on the things we can find, the thing we need to first look at is the chi-square difference test. For a WSMV estimator, we request the diff test from Mplus, and we use alpha equal to 0.05. And the next thing we look at is the model modification indices. I will show you what it looks like later. And these 2 are the most important thing to look at when you deal with WSMV estimator. But when you look at ML or MLR, you could also look at the change on CFI, TLI, and RMSEA. These are practical fit indices. So the problem here is that the limitation is for the chi-square difference test, it is sensitive to the sample size. So it is possible with a large sample size, the possibility of making type 1 error increase. But for the last set, the change on CFI, TLI, and RMSEA, they are not sensitive to sample size, but sometimes they are not powerful enough to detect measurement non-invariance. So basically, we need to look at all of them together and make your judgment based on the theories and every criterion. Okay, here is the syntax we used to test configural invariance model. So this is the first part of the syntax. All the syntax belong to one file, but I separated them out for demonstration purpose. So basically, we give a title of the syntax, and we specify the data. We tell Mplus which data file we are looking at, and we define the variable names. Names are sex, A1, B1, C1, and D1. These are the items, or the categorical indicators. And we define that we use all of the variables in this analysis, and the grouping variable here is sex. So there, we also need to tell Mplus what number represent which group. So 0 represent female, 1 represent male group. And we also need to define these are categorical data, not continuous data. Then we define the missing value. So for categorical data, we use a corresponding estimator, WSMV, weighted least square with adjusted mean and variance. Then the last 3 lines in the analysis, you can just use default information, or you could define it or change it with your knowledge. And the last thing is the output part. So sample stats and the standardized solution are things you typically request from Mplus. One thing we need to emphasize here is the mod indices. This is something you need to specify so that Mplus can provide.
Actually, the coverage and iterations can be ignored if you want to just use the default feature of Mplus. When you are doing measurement variance with categorical items, you have to specify the items of categorical are which items. And because you're actually going to be looking at residual variances, which get estimated a little differently in Mplus, you have to specify under the analysis stage that the parameterization equals theta. If you do not, and you try to actually estimate residual variances, you will get an error message stating that you need to change your parameterization to equal theta.
And for continuous data, how does this look?
You
What would
need
look
to-
different for continuous?
For
data?
continuous data, there is no line for categorical, so the categorical R is not there, don't need to have that. And the estimator could be ML. Yes.
And then parameterization struct,
Yes.
iteration struct, coverage struct.
Okay, still from the same Mplus syntax file, and I put this both file. I put them on 2 sides, but they're actually in one file. Okay, for the first model is the reference group, and it is used as a baseline model or reference model. So the baseline model is using the grouping variable equal to 0. So basically, in my case, it's all the goals. Okay, then we specify the factor by A1, B1, C1, D1, basically all those arrows we showed earlier, all the red arrows. And we also we give the name of the parameter, loading A, LA, loading B, LB, etc. Okay, then it's the item thresholds. We specified all the item thresholds to be free. So thinking about this graph here, so for a full category item, we will have 3 thresholds. So A1 $1 means the factor threshold for first item A1. A1 $2 is the second threshold for item A1, etc. And we, since we freely estimated all the item factor loadings, there, we need to specify something. We need to constrain something to make the model can be identified. So the factor means are 0, factor variance are 1 for model identification purpose. And the item residual variance are set to 1 at this moment. And here are two things. And then we repeat all those commands for the model M. Model M means it is using the grouping variable that equal to 1, so all the boys. The difference between the red square, the thing marked there is no name under that one, which means all the factor loading, although the arrows are the same, the factor loading estimation were freely for both groups. Okay, then one thing we need to do is to save all these estimations for this configural model, save it as configural.dat. That is for later comparison.
If you were doing this with ML estimation, okay, this syntax would look drastically different, and it's too much for us to comment on it right now. Okay? But just as a note, if you're trying to switch over to ML, it's WWSMB, there's a lot of things that would be dropped, but it's too much to comment right now for you.
Okay, here is part of the output we want to look at. Basically, at this stage, we want to make sure this models we just set, it has a acceptable to good global model fit. We look at the chi-square as the first square is 0.000. It means by comparing this model fits the data, does not fit the data. So, but we know that the chi-square for WSMA is sample dependent and it is sensitive to sample size. So we keep looking other practical fit indices. Then we look at the RMS-EA. If we compare it with the 0.05 criterion, it does not fit the data as well based on RMS-EA. And if we look at CFI and TLI, we found that by using the criteria 0.95, the model data fit is good, is acceptable. So we also look at the weighted root mean, the bottom line, weighted root mean square residuals. When it is below 1.0, it means the model data fit is acceptable or good. So we have evidences showing that the model data fit is acceptable. So we proceed to the next step. We set up the weak factorial invariance model to compare it with the configural model. Cameron, do you mind to write down the RMS-EA values? It's 0.086 for 0.086 for the configural model, and 0.999 for CFI, 999 for CFI, 0.997 for TLI. Then we will compare these values. Okay, so for weak factorial invariance model, at the analysis command, we add one line. Diff test is, it tells Mplus which previous model we are going to compare with. We're comparing with the configural model. And at the bottom here, save data, we save this new data as weak. So we basically will compare weak with configural model. And one more thing we set up here is the left side I kept the same for configural and weak factorial invariance model, but for the model M, for the focal group, now we put the same name, LA, LB, LC, LD, for both group factor loadings, meaning that this we add the constraints on factor loadings. We force them to be the same. So we're going to see by having more constraints whether the model fit dropped. Okay. Here is the result we are looking at. We are looking at the chi-square difference test first. So by using the 0.05 alpha level, we found that the model fit became significantly worse than the configural model. Okay, then we look at the RMS-EA. Now the RMS-EA value is 0.058. And the CFI is 0.999. TLI is 0.999 as well. So actually, we found that based on the practical fit indices, the model fit actually improved by having more constraints. So we can, and the WRMR is still below 1.0, meaning this model has a good model data fit. So we consider this current tool, we use this 4-item language tool, hold weak factorial invariance. And we also look at the model fit modification indices. Here we are looking for bias statement. So if here, is there anything showing that fact by A1, B1, or C1, it means these item factor loadings need to be set free instead of being constrained. But here we don't say that, meaning that the modification indices didn't suggest to free any factor loadings, which also confirm what we found in the previous step, previous output here, that our tool holds weak factorial invariance. Okay, so then we can move on to the next step to test the strong invariance model. Again, the part highlighted in red square is we changed the test to weak invariance model here. Now we test the strong against weak. Okay, so at this step, all the item factor loadings are still constrained. But for the model M, for the focal group, we set the thresholds to be equal with the reference group. So if you left anything to be blank, it means it is only for the item thresholds. So if you don't specify it, it will use whatever you have for the reference group. Okay, then since we have more constraints over there, we are able to free factor means and factor variance. This way we can estimate whether if you recall the diagram, the phi 1 and phi 2, we can test whether phi 1 and phi 2 are comparable for both groups. Okay, at this step, we first still look at the chi-square difference test. The p-value is above 0.05, it is 0.40. So based on chi-square, we can say that confidently that the model fit does not get worse by having all the item thresholds hold to be equal across groups. And yeah.
I got it. The pen's running out.
Okay. Then we look at the RMSEA, CFI, and TLI. The RMSEA continually dropped. So it's basically all suggesting that by having more constraints hold equal for boys and girls, the model data fit improved, but not for the WRMR. And we also look at the modification indices. Here, especially for the group M, if there is anything needed to be freed, it will show at the group M section. So we are looking for some dollar statement, which means whether any of the thresholds need to be freely estimated for the M group. But we don't see any. It also confirms that this tool holds strong invariance. Okay, so the last part of this test is to test the strict factorial invariance model. So here we need an extra step to perform this test. If you notice that at the analysis part, we don't put any diff test there because this is like a side step to set up the test for testing item residual variance. Okay. So at this part, at the one of the two set steps for testing strict factorial invariance model, we set everything else hold the same as the strong invariance model, except for for that part. All the item residuals set to be free for this side model. But for the second model, we set up this to be equal. So basically, we add constraints on the item residuals, and we compare whether this model fit worse than the previous model that had all the item residuals to be freely estimated. So we're comparing the strict B with diff test at the last line of analysis. We're comparing strict B with strict A. Then again, we still look at the chi-square difference test. The p-value is promisingly above 0.05, suggesting that this model, this tool, can hold a strict factorial invariance. It's the same idea for the RMS EA change, CFI-TLI. And here, well, if there is anything needed to be free estimated, you will see if C1 needed to be free, it will say C1. But since there is nothing shown, it also all the evidences pointed that this tool holds the highest level, highest degree of measurement invariance. So as a conclusion, we find evidences for this language measurement tool that it holds the strict factorial invariance. So we can confidently make any comparisons between boys and girls based on these 4 items. And all the differences we found is due to the real gender difference instead of any measurement errors. Time for questions?
Can we just go back to the syntax for the weak factorial law?
Sure. Yes.
I just want to look at, so I was wondering why it's in the process to get why the factor variances were set free for males.
The thing is, when you have more things set constrained, you are able to test the more things. So since we had factor loadings to be equal across
Factor
groups,
variance.
that it can be free. Yes, yes. This is also why here at the implication that we can test variance and we can compare variance and covariance.
Can you go to the configural? Yeah, the output data.
Output?
Yeah, no, actually, you're right. It's sorry. Can you just explain really quickly why I see in parentheses the LA, LB, LC, LD, and I understand why you don't do it on the model of interest, so the boys, is that for the boys?
Yes.
But what does that mean, the letters? I guess I don't understand what this.
This
The
part?
The
LA.
LA, LB, LC, LD.
It's the loading for A, the loading for B, the loading for C, the loading for D.
Yeah, basically we give a name of it. At this step, you don't need to have it, but when you do the weak factor invariance, when you have the same parameter name, it means they're equal. So LA for girls, LA for boys.
Okay, I see
Yeah.
that. So you're just naming.
Yes, the naming part tells Mplus they are the same. They will be estimated equally.
Huh, okay.
Yeah.
You just copy and paste it over.
You could.
Okay.
Yeah.
Other questions? All right. Well, Dr. Zisha Lee and Dr. Caroline Gooden, thank you for giving this talk today.